Okay, so we were just discussing the fact that delta is Lorentz invariant. So now, just to make the concrete a little bit more, the calculation a little bit more concrete, I'd like to consider a Lorentz transformation, which takes x mu into lambda mu nu x nu. I might just write this as lambda x mu, and I might write it without 4 vector indices at all, and just say x goes into lambda x. Lambda could be a boost, the boost matrix that we were studying before, or it could be a rotation. Anything like that would be fair game. Now let's study delta of lambda x. So what is this equal to? Well, this would be equal to an integral d3p over 2 pi cubed to omega p. And then we would have e to the minus I p dot lambda x. So now let's change integration variables from p to k, where I want to have p equal to lambda k. Okay, so this 4-vector equation, p is equal to lambda k, you would pick up the px component, the py component, and the pz component. That would be written in terms of kx, ky, kz. That would be the change of variables. And if you do this, what will you find? Well, first of all, because p and k are related by a Lorentz transformation, you know that the measure will be completely unchanged. Okay, we have verified that. So the measure stays unchanged. And here we would have e to the minus I, and instead of p, we would have lambda k dot lambda x. But remember that 4 vectors are invariant under Lorentz transformations. So that means if you've got lambda k mu, lambda x mu, this will just be k mu x mu. So in actual fact, what we learn is that delta of lambda x is equal to an integral d3k over 2 pi cubed to omega k e to the minus I k dot x. And this is just delta of x. Okay, so that's what we mean when we say that delta is Lorentz invariant. Delta of lambda x is equal to delta of x. So there's a very precise mathematical statement for what it means for this function delta to be invariant under Lorentz transformations. Good. All right. Now I would like to use a fact that I'm going to state. And this is something that you're going to prove in the exercises. So I'm certain that you can prove this. Think about it. It's a nice thing to prove. So if x and y are space-like separated, okay, let me immediately make this clear. If and only if x and y are space-like separated, then there is a Lorentz transformation which takes x minus y into minus x minus y. So what that means is, if x and y are space-like separated, you can find a Lorentz transformation so that this is true. If x and y are time-like separated, there is no such Lorentz transformation. And if x minus y are null separated, light-like separated, there is no Lorentz transformation. So very important, this holds only when X and Y are space-like separated. So that's an important qualifier. But what does that mean? So we proved that phi of X and phi of Y was equal to delta of X minus Y minus delta of minus X. Sorry, let me just good. Minus X minus Y. Okay. So we proved that. So if X and Y are space-like separated, by the way, this commutator result that we obtained holds for any X and Y, not necessarily just space-like separated. But if X and Y are space-like separated, then we know that delta of minus X minus Y is equal to, in this case, there is a Lorentz transformation, which will take X minus Y into minus X minus Y. And because delta is Lorentz invariant, that means delta of minus X minus Y is delta of X minus Y. And that means, look back at our commutator, it means that phi of X and phi of Y commute. Okay? So we have now verified that our first axiom holds. And this is the field that does it. So this is our scalar field stated right here. Let's maybe clean this up a little bit. Okay, good. So here is our scalar field. There's the definition of it. And I simply need to tell you what are the harmonic oscillator operators. And they are defined by these commutation relations. So this is the answer that we've obtained for the free scalar field. And in what follows, our goal is going to be to understand this answer that we've got, to understand the free scalar field in as much detail as we can, and to be able to interpret it. But what is it equal to? Phi of X is equal to this Lorentz invariant integration measure. We've got an e to the minus I k dot x multiplying alpha k, the creation operator, the annihilation operator. And then we've got e to the plus I k dot x acting on alpha k dagger. K dot x is omega kt minus k dot x, and the oscillators are defined by those commutation relations. So this is what we've managed to prove. And where did this field follow from? Enforcing our 5 axioms, which seemed very natural. And remember what they were? The field should commute with itself at space-like separation. The field should be a Hermitian operator. It should transform in the correct way under translations. It should transform in the correct way under Lorentz transformations. And our final condition was that it should be built out of the harmonic oscillator creation and annihilation operators, because we were dealing with the free field. Great. So now we can start to do a little bit of quantum field theory.